Okay, great. So good morning. It's a pleasure to be here. And I want to thank the organizers for inviting me back to ICAP. It's been a wonderful meeting, and I'm really enjoying my first visit here to Korea. So indeed, what I want to do today is tell you about work by our team at Yale on using these exotic cat states of microwave cavities for quantum information. So this work is part of a team effort. There are several research groups at Yale all working together and contributing to this work. And just, I'll point out that disclosure for you to take note of. Okay, so I thought I'd start with a bit of a general outlook because this has been coming up in discussions at coffee and things with people. Like many of my colleagues in quantum information now, we're pretty optimistic really about prospects for building interesting and eventually useful quantum information processing systems using these kind of technologies. I think he's heard a similar kind of perspective from some of the ion trap people earlier in the meeting. What do I mean by an interesting quantum information system? That's one where we will have, probably within the next 5 years, 30 to 50 degrees of freedom that are all entangled. And that's something which cannot ever really be classically simulated. Now, to get there, to scale up, right, there's going to have to be an increased push on technology. We're going to have to bring in people from other disciplines for the systems engineering and support stuff and information theory to tell us what algorithms eventually we want to do to be useful. But you'll hear some people in the field saying, oh, well, we have a scientific proof now in the lab that everything could work, should work, so it's time to just put our heads down and engineer, and the science is over. And that's a very silly, to me anyway, point of view, right? Science never ends and becomes engineering. What happens is if a discipline actually has potential applications, you start ramping up the applied side. And if you do it right, that just further enables and accelerates the really interesting basic science. So we shouldn't just try and blindly scale the first thing we think looks like it could be a scalable quantum computer. We should always be thinking what's the easiest, best, and most clever way. And I think there will always be really interesting scientific questions that I hope to bring out here that will keep people like us motivated. So it doesn't just make a bit flip from science to engineering. So why are we so optimistic? Well, remember in the beginning with our kinds of superconducting systems with artificial atoms, it was far from clear when I started my lab that we'd ever be able to make a man-made object that would have a simple Hamiltonian, much less one that would get you invited to talk at ICAP. Furthermore, it was unclear that we'd ever really be able to isolate these things as well as atomic systems can be, for instance, and to get really long coherences. And so there's been this remarkable sort of more than 1 million-fold now improvement in the coherence times of these superconducting quantum bits. And it hasn't rolled over yet, so we're optimistic that it will continue to improve. And now, as I'll show you later on, we're able to entangle multiple degrees of freedom that have millisecond or multiple millisecond coherence times. The time it takes us to do an elementary operation is in the tens or hundreds of nanoseconds. So certainly this means we may well be already passing the quantum error correction threshold, and the ability to scale is there. But of course, you always want the coherence to get longer and to be able to do better operations. Now, there's also been remarkable progress in lots of other aspects in the reliability of these systems, our ability to design complicated things in this quantum domain, the reproducibility, but especially also in the area of measurement. So what this is showing is 2 time traces here, which are continuous measurements of one of these transmon qubits showing individual quantum jumps. And in the beginning, it was very difficult to even detect whether we'd done a pi pulse on one of these qubits. So now, almost every experiment in our lab uses this sort of single-shot quantum jump measurements at the end. And that's been enabled also by a lot of interesting science and technology, especially my partner, Michel Devoret at Yale, has been driving this development of quantum-limited microwave amplifiers, which are used to basically obtain this kind of signal-to-noise. And this is now something which begins to be like a commodity. We have almost 24 of them in use around the lab. Not every student even knows how to build one themselves. And so in this new venture, we're actually making these commercially available to the rest of the research community. 12-week delivery time, and you can do quantum-limited measurements of a 5 or a 7 gigahertz microwave signal in a Dilfridge. So, all right, let's say that we want to build fault-tolerant large-scale quantum computers. Again, there's lots of interesting physics along the way. How is everyone doing on this? So we, not just our group, but as a species, and with several different kinds of qubit technologies, are maybe sort of here in this notional platform. So we have the ability to make coherent qubits. We can manipulate them and entangle them and do simple algorithms. We can do quantum non-demolition measurements, especially on a subset of the system. And that means now, as you heard again in some of the talks by the ion trap people, that we start to think really about the issues of quantum error correction and making what are called logical qubits, something where we redundantly encode one superposition, a bit of quantum information, and we run a quantum error correction algorithm to try and compensate for the negative effects of the environment. And so what I wanted to do today and the rest of the time here is, well, since I think the first one speaking about this, I'll give a really quick reminder of how these quantum circuits work. I'll introduce this hardware-efficient approach for error correction that we like. It's called the CAT code, where we use multiple photons in a microwave cavity. And then show you a result which just came out last week in press, which is implementation of a quantum error-corrected memory that actually can track the naturally occurring errors and extend the lifetime of information and reach the break-even point. So it's just the very beginning of doing quantum error correction, but we were quite excited, and I think it really makes QEC a very tangible and hands-on kind of experimental discipline for us. And if there's time at the end here, I will also show a little bit of future things. So this cat in two boxes, or making a Schrodinger cat between two different separate microwave cavities, which you can think of as entangling two logical qubits of these types, and some operations on single qubit devices, single logical qubits. So for all these quantum circuits, the element at the heart of them is a Josephson junction. Basically, that is just a nonlinear inductor. And to make a so-called transmon qubit that's very popular these days, we just add a linear capacitor, and then we obtain a sort of electromagnetic oscillator with frequencies in the 5 to 10 gigahertz range. Work in a dilution refrigerator. We are mostly polarized in the ground state at the beginning. And due to the Josephson effect, we have really not just a conventional harmonic oscillator, but we have this cosine potential, and the energy levels are unequally spaced. Typically, the anharmonicity, or the frequency difference of this transition from the ground to excited state of the first two levels, is a few hundred megahertz, and that's a large energy scale in the problem. So we can, to a very good approximation, just call this thing a two-level system here, and there's some energy, again, of a few gigahertz between the G and the E. So that's our nonlinear element. And then we've been having a lot of fun following the lead of quantum optics and cavity QED by combining these qubits with various kinds of photons in microwave cavities. So they can be transmission lines or what have you. As again was mentioned earlier in the sessions on cavity QED, the goal right here is to get to the strong coupling regime, where the vacuum Rabi frequency G is larger than all the decoherences. And it's sort of cheating in this system, frankly. So with our qubits, we can have dipole moments that are an electron micron to an electron millimeter. We get very, very strong couplings. Typically, G is a few % of the overall transition frequency. We've kind of always been in the strong coupling limit. And if you want to even think of it, the cooperativity these days is in excess of 10 to the 10. And over the years, to improve the lifetime, the sort of form factor and the way we make these things changes. Again, because these devices interact so strongly and they have such strong nonlinearities, we worry about a whole lot of things. There are materials issues as well, but also you have to worry about spurious modes, radiation, even the loss from seams in your package. So here's a kind of cross-section. It's been destructively cut in half to show you the guts of a single block of metal, which has a little popsicle stick of sapphire containing a qubit, which can couple to multiple cavities that here basically are sort of lambda over 4 three-dimensional coaxial posts, again, to give a resonance in the few gigahertz range. And the interactions between this transmon and the cavities stay the same. It's, even the dispersive interaction can be, the second-order Jaynes-Cummings can be several megahertz. And so today we can, with these kinds of devices, reliably get coherence times of the transmons of nearly 100 microseconds, and of the cavities, T1 and T2 can both be in excess of milliseconds. So now, before I show you the experiment on quantum error correction, I need to remind you a little bit about how it works and what you should look for when you build a system like this. So first off, to do error correction, what we have to do is redundantly encode information. And I'm showing here the kind of one of the canonical ways of doing that using 7 qubits. You saw some beautiful results from Rainer Blatt's group on actually encoding states in 7 physical ions to make up this kind of logical register. And then basically what you have to do, because all of these qubits can be undergoing errors, is you need these 6 ancillas and this complicated sequence of gates so as to measure the correlations or the symmetry properties of the state you encoded in and decide whether an error has occurred and what error it was. And so this is a significant jump in complexity. Now, it would be possible to do that with sort of 7 transmons all coupled to each other in a cavity and 6 additional transmons to be the ancillas and readouts and parametric amplifiers for all of those. But it would be a lot of work, and maybe there's a better way forward. And I also want to point out that one of the challenges here is not just the complexity. Of course, as you know, things need to work really well. So because of this complexity here, you can imagine that it takes a time I'll call TM, which is not negligible, to actually do this whole circuit and record whether an error has occurred. And this is just a first-order code. So we need to have each round of this error checking occur much more rapidly than an error can occur in any one of these elements of the device. And so there's a kind of downside which people don't usually talk about in quantum error correction. So the redundancy means you can compensate for errors. However, by storing among these 7 qubits, now there are 7 times as many ways for things to go wrong. And typically, the first error will happen 7 times faster, even if every member of your register is as good as your best single physical qubit. OK, so, and again, because it's a first-order code, you won't turn on error correction, and the lifetime will be immediately infinite. What you hope to do, of course, is to reach this break-even. So again, if we would store a superposition in some physical qubit, let's say there's a characteristic error time T1, we would get a decay. If we then redundantly encode, we'll have a faster decay. If it's the 7-qubit code, it would be 7 times. Here I'm just showing a factor of 3, which is closer to the overhead in the scheme we use. And then if we run at each time step TM as quickly as we can, our error correction, what we hope to have, right, is a compensation of the errors, but we will still have a failure because there's some finite probability that there were 2 errors during that sequence. And so our fidelity will still degrade at a rate that's given by this, and basically we have an effective lifetime of this first-order code, which hopefully can be enhanced and can go above the lifetime of our best physical constituent, but only if we can really measure much more quickly than this error time t. And basically, this is where these error correction fault tolerance thresholds come from, the fact that they need that gain to be larger than 1, and therefore the fidelity of the operations or the error rate to be very low. So what I want to show you is a scheme here where we can do a simplified version of this. So we want to use these very high Q cavities as our register to be the logical qubit. And we know, for example, that they have one main error syndrome. That is, the Q is only about 10 to the 8 today, and so we can suffer single photon loss. And basically, with a certain code that I'll now describe, we can use a single transmon as an ancilla, a single channel of readout, and detect when these errors occur and try to compensate for them. And since we'll use a kind of cat state here with an n bar of about 2 or 3, we will have a lifetime penalty or a sort of overhead of our quantum error correcting redundancy that's in the range of 2 to 3. So we want to see if we can make that up. So how will we encode in the cavity? Well, the obvious thing would be to use just 0 and 1, the presence or absence of a photon. But of course, if we have photon loss, 1 turns into 0, and everything is over. Now, we could use coherent states. Those will still be distinguishable when we have a single photon loss. But we still don't have a sort of symmetry that we can really check that would tell us whether an error has occurred without telling us what superposition we've stored. The interesting thing here is to look at these kind of cat states. Symmetric superposition, for instance, of 2 opposite phases for coherent states in the cavity. This is an eigenstate of photon number parity. It contains sort of Poisson distribution, but of only the even photon numbers. So what we do in the cat code is basically we use a horizontal cat in X and a vertical cat in P, if you like. For large enough beta, these states are essentially orthogonal. We can make that very negligible in these experiments. And then we can have a sort of logical block sphere that consists of all the possible superpositions of these two cats. In general, they will look like this. These are cartoons. You'll see data in a minute. And a nice property here is that all states on this block sphere have, let's say, even photon number parity. And you could equally well do this with the antisymmetric superpositions. They would have odd photon number parity and a different color blue in the center of these Wigner functions. And that'll serve as basically the error space for this code. So how does the code work? Well, let's say we've encoded a superposition of these even parity cats. The initial Wigner function might look something like that. If we wait, at some point in time, a photon is lost. And what that does is it changes the state, you see, from red in the center to blue. The parity changes, and we can detect that. It also induces a sort of transformation on your quantum information. It pulls out this factor of I, which is like a 90-degree rotation around the z-axis here. And if we wait a little longer, there might be a second photon loss, another factor of I. If you continue this game, it turns out after 4 photon jumps, because these states are invariant under a to the 4th, you get back to the beginning. So if these jumps happen and we don't know about them, then they're really a loss of information. But if they happen and we know, we can compensate for that, either by correcting it in the device or just remembering that in our algorithm. Now, there's a second thing that happens, of course. Even in the absence of jumps, eventually the energy leaks out of this cavity, and our coherent state amplitudes decay away. In this experiment, we're not dealing with that yet. We're just going to work at a time which is short enough that the coherent states don't actually overlap. So to measure the parity, we're going to steal a march from the Rydberg atom cavity QED. This wonderful book is on every bench, and it's been really, really useful. So what you can do basically is a Ramsey experiment, and this was also discussed by Stefan Ritter in his talk yesterday. So if you do a pi/2 pulse, and we're in this dispersive limit of cavity QED, so the transmon and the cavity are detuned, there is still an interaction chi. There's a quantized light shift for every photon in the box, which is, let's say, a megahertz in our case. And so after a certain amount of time, you get a sort of dispersion of your blocks vector for the transmon on the equator here. The red and the blue indicate even and odd photon numbers. If we wait the right amount of time, pi/chi, which is a couple hundred nanoseconds for us, then you get this kind of aligning of all the even and the odd states. One more pi/2 pulse, and now if you measure the state of the transmon, you know whether the photon number in the cavity was even or odd. But you don't know the photon number, and you don't know what superposition you might have encoded in your 4-cat. So earlier we showed that we could do this kind of projective QND measurement. We could record nice quantum jumps of the parity. Interestingly, these are a little different than the usual quantum jumps of an ion or of a photon number in a box. These are not jumps between energy eigenstates, but between two different subspaces of a higher dimensional system with, again, the even and the odd parities. So the time it takes us to measure is about a microsecond. In the implementation of cavities here, which is a little older, the error time between jumps was on the order of 100 microseconds. The fidelity of each individual measurement is something like 98%, and there's an almost negligible probability that we actually absorb a photon or cause an error in the process of making this measurement. And so this means we have the resource to actually do error correction. Let's see if we can get it to work. So what we're going to do, again, I want to emphasize, we need to correct a superposition. Any state on this block sphere, you're handing it to me. I'm going to store it in my device and hopefully return it to you with a better fidelity because I'm doing error correction. So we take any one of these 6 points on an octahedron on the block sphere. We encode them into the appropriate 4-component cat. We wait a certain amount of time. We perform a sequence of measurements to monitor the parity and record whether jumps occur. And then adaptively in real time, we need to decode, know the number of jumps modulo 4, apply a correction, and we'll do process tomography on the result. And basically, we're trying to do a really simple function in error correction here, just identity, but actually get that to work. So there was a lot of technology, which I don't have time to go into, but the guys deserve many kudos for getting this to work. Our own custom FPGAs to do all the control. I think all the Wigner functions from here on are 100% data, believe it or not. And so this is too complicated to go through, but just to give you an idea of how complex this is, we can actually run what I call the debugger view, and the controller is deciding on its own in real time whether it thinks an error has occurred. And one advantage of this simpler error correcting system is we can actually fully characterize at each point in the trajectories what the state of the system looks like, and really kind of get under the hood and see how this works. And it all basically works just according to what we expected given the properties of the system that we knew independently. And so at the end, we're going to take all the data. So there's some number of jumps. We will have differing fidelities for these things. We'll combine them all together. And this is what we see. So again, there are many ways we could physically encode this superposition or this bit of quantum information. If we put it in the transmon, of course, this is an ancilla transmon. It's not very long-lived, and things decay away to the ground state pretty rapidly. Now, we can encode in this 4-component cat in the cavity, but not run the error correction, and then you see that the information still decays. Now, it decays more slowly, but that's not the gain we're talking about. That's just a passive thing if we made a better memory. But then the remarkable thing is if we actually run the error correction, still after 100 microseconds, you can see that this information is decaying as it needs to because it's a first-order code, but it's decaying more slowly, and I hope you can see that this is still a more pure state than the one where we don't run the error correction. So quantitatively, we can sort of look at this. Again, to reach break even, we say we want to surpass sort of the best physical constituent in our system, which would have been using the 0-1 Fock encoding and measuring just the lifetime of a single photon in a cavity. Here's the uncorrected cat code, which suffers this penalty. This is the overhead penalty here, about a factor of 2. And when we run the error correction, we get back that factor of 2 and just a little bit more. So we're just barely at break even. If you let us play some other games and throw away bad measurements, we can sort of do some post-selection here and get an even longer lifetime, but this is not really fair and not usable in a scalable computer in general. So, okay, obviously it needs to work much better than this, but still we were very happy that this error correction works, and we can sort of understand the performance of the system in the lab and at the bench. And something we didn't expect was actually what the real limitations of the system would be. So as I said, we can measure kind of 100 times per typical error. So you would have naively, in this kind of code, expected that we would improve the lifetime by an order of magnitude or 2. However, and unfortunately this is a problem that everyone's going to have even in those 7-qubit codes, if you actually do this measurement as drawn or in the 7-qubit code, it's not yet fault tolerant. That is, we're not doing a measurement of the syndrome that is insensitive to the errors on the actual physical ancilla. So in general, in error correction, you have to correct all the way down. Every element needs to be corrected, and that's something that's not yet put in here. And so what that meant, if you noticed, we were actually measuring much more slowly than we had to so as to reduce this, and at the penalty of course, increasing the other kinds of failures of the code. Okay, so I think I just have a few minutes left. I want to leave some time for questions. So let me just quickly tell you about this other experiment, which is something where we take 2 of these high Q cavities, and now we have a device we call the Wymon. So this is a superconducting qubit that has sort of 3 horns, and it couples simultaneously to these 2 high Q cavities and to a lower Q readout resonator. And what we're going to do with this, although I won't be able to tell you the details, is we can create a superposition of cat states that is distributed between the 2 boxes. So to remind you, in a single mode cavity, you have beta plus minus beta. That's an eigenstate of photon number parity, and you measure the Wigner function to learn the density matrix of that system. If we have 2 modes and we can make this kind of entangled cat, either the cavity Alice and the cavity Bob are both alive or both dead, that is actually an eigenstate of the total photon number parity. So the number of photons is not well determined. It's Poisson distributed. The number of photons in Alice is neither even nor odd. The number of photons in Bob is neither even nor odd. But the sum of their photons is actually even or odd. And so you need to measure this joint Wigner function in order to characterize that state, which is what we can do with that Wymon ancilla. And so, believe it or not, here is the measured joint Wigner function of that state after we create it. Here we have a beta of about 2, so there's about 16 photons of distance between these coherent states. And this, overall, this system lives in a very high dimensional Hilbert space of about 150 D. So to characterize, you need to look at this complete 4D space, but here's a cut, let's say, along X of Alice and X of Bob. What you see are blobs here that tell you the correlations in the phases of the two cavities. There's a negativity here at the center, which tells you it's really a quantum state. And then you see this sort of evidence of the cats shows up in sort of the P versus P for Alice and Bob. Here are the fringes, which again get smaller and smaller as we move the blobs apart. So this is really neat. Just to convince you it's really data, here's line cuts comparing the theory and the ideal. The fidelity is, I forget, something in the range of 85% here in this first implementation. And another thing we can do here is really show that the two cavities are actually entangled. So again, following a prescription, this has been a holy grail, right, for cavity QED for some time. Basically, you can look at different points in this joint Wigner function and sort of look at quantities you construct out of this, which are analogous to a sort of CHSH inequality. And what we can measure that, by the way, all this data is uncorrected for any measurement fidelity or anything like that. And we can see a very convincing violation of the classical bound. So it's not a loophole-free or anything Bell test, just a way of characterizing whether the state is truly entangled. So I'm not quite sure if the timer's on the right state. Maybe the other thing I'll say, since the chairman's not standing up yet, we've also had a series of papers looking at better and better ways to manipulate the cavity in complex and arbitrary ways. So it sort of was obvious how to make superpositions of coherent states using this dispersive interaction of the qubit and cavity. But let's say we want to do something very non-trivial here and actually go from, let's say, the vacuum to the Fock state number 6. And again, because we have the nonlinear transmon, we have controls where we can drive both the transmon and the cavity, and because the two entangle with each other, we actually have a very powerful system. So what we do is we throw a computer at it, we use the techniques of optimal control pulses, or optimal control engineering from NMR, and computer spits out something like this. It says drive the transmon and the cavity like so, with some seemingly random looking wiggles. It drives the system from probability of being in 0 to probability of being in 6. You see it here. That's the measured Wigner function of the resulting state. And in addition, you can actually manipulate these 4 component cats inside the cavity. So here's us doing sort of a Clifford operation on the logical. We go from z to y to minus z by applying rotations successively around x. And we can do randomized benchmarking on these, and it already works at fidelity of 99%. So now he's standing up. I want to thank all the team members in the lab, and I'll just put up the summary and ask for any questions. Thanks.
OK, thank you very much. So I open this for questions. There's one here already at the back. One further back, but we can start with Rainer.
Thank you. Can I start?
Yeah.
Very nice work, Rob.
Thanks.
I just would like to know, are there any correlated errors in your error budget that you have not accounted for, or that you have accounted for, or to which extent do they contribute to the error budget?
Right, so this is a good question. So in a way, photon loss in the cavity amongst the n states is a correlated error, but it's correlated in a way that is good for us and we can sort of deal with. If you like, the sort of limit on the performance of the error correction is this feed forward of the error. It's the fact that errors in the ancilla come in, and that does create sort of correlated errors amongst the n photons because the ancilla was entangled with all n photons at once. Now, as far as we know, and as far as we can measure, this photon loss is by at least an order of magnitude, or maybe a factor of 30, the dominant error process in the free-running cavity all by itself, if we take away the effects of the ancilla that it's coupled to. So I don't think that's a big problem for now. I mean, we have to sort of work our way up in these things. And also, these 4-component cats are just the beginning, so we're having a lot of fun thinking of other kinds of codes. So you can make higher-order codes that are robust against double jumps or jumps of both A and A dagger, which does happen at some level in our system. And you can also make codes that are robust against dephasing. Now, you're not going to make an enormous code inside one oscillator, but I think there's still a lot of room to play around.
the superposition state of the coherent states, what is the trade-off between the amplitude that you use? Because the larger the state, the faster photon loss occurs, but then you have also distinguishability problem. What is the optimum?
Yeah, that's
size?
right. So, so first of all, you need enough separation of your coherent states that they're effectively orthogonal. But that is like a Gaussian function. It's very, you only need to go to alpha of 2.5 or something like that to really be as good as you would ever want. In this experiment, we used both n bar of 2 and n bar of 3 and did the error correction, and the performance was just about the same. So you have a higher overhead of 3, and then you make up a little bit more. It sort of is not a very sensitive number here. But yeah, I mean, if you want to play these games of doing more complicated codes, you want to give yourself more space. So I think, again, there's room to play, and especially I think we haven't seen the limits of how good these cavities can be. Again, the Paris guys have seen 100 times longer lifetimes in their kind of cavities. So I think that means you could afford to increase your space somewhat. Need to worry about higher order terms in the Hamiltonian, though. That's something I didn't really talk about. It's there, and it's important.
Okay, is there maybe one more quick question? Okay, again at the back. Yeah.
Oh, yeah.
So now from your experiment, we can see that the fidelity, the gate for gate operation, you have like 99 or maybe even higher, and from the coherence time, it's somehow like you can apply thousands of gates already. So what is now for the quantum error correction? There must be a threshold. How far away that we still should work until we have a circuit that really works for quantum error correction?
So this question of threshold is a really interesting one, and it depends, of course, on your error correcting code and the architecture you're going to string these things together in. And also, we need to be careful about the difference between just, how quickly a Rabi flop on a single qubit decays and how quickly I can do a very accurate entangling operation between 2 qubits. And moreover, if you want to do sort of the analog of this logical manipulation in the 7-qubit code, you have to manipulate all 7 qubits, okay? So that's something which is, again, more demanding. These fidelities here are essentially limited, or they're consistent with the limit we expect from just the finite lifetime of the transmon ancilla, which is used to manipulate them. So, and the issue here is that to do this very complicated manipulation, we slow down a little bit. This operation takes typically sort of 500 nanoseconds, whereas on a single qubit, you can do operations in 20 nanoseconds or something like that. So there's a trade-off here, and basically as your coherence gets better, right, you should have a better error, but then typically you need to make the precision or the accuracy of your manipulations really better, which means you usually need to have more precisely shaped pulses, and you often need to slow down. So just like increasing the coherence time by a factor of 10, maybe you're able to increase the overall fidelity, but maybe not always by a factor of 10. So I think you still need lots more work on coherence. So.
Okay, I think we definitely have to move on, so let's thank Robert again. And now the next talk will be by Wuming Liu from the Institute of Physics, Chinese Academy of Sciences, and he'll talk about Rydberg atoms in a cavity. So please welcome him to the stage.